here today can see what we're doing. So we're going to try to analyze this circuit box, analyze another complex circuit. So again, if you're watching this video because you're gone 419 this Friday, I'm going to analyze some complex circuits, and then we're going to do some whiteboarding. Okay. I don't intend to give you guys a lot of homework this weekend, but I might give you a problem to try on your own regarding complex circuits. All right, let's take a look at this. And you guys, what I would like to know is how this is wired. Okay, so I showed you guys this, I think, in the beginning of this class, and so I'm first just going to pull out the 1, and you guys notice that what that does is it takes out 2 and 4. I pull out the 4. You see that pulls out the 1, 2, and 4, and I pull out the 2, and that knocks those out. How are 1, 2, and 4 wired? Just turn and tell that person that you're sitting next to. You guys agree? Yeah. Okay, 1, 2, and 4. I'm going to ask you guys actually to write that. I want you to actually draw the circuit for me. So in your note packet, just you're going to have 3 different circuits that I want you to try to write. And so in your note packet, let's see. I'm not sure where this. I gave you guys purple for this. All right. So where could you do this? I'm going to say try this. How about this right here? Since it's similar to series and parallel kind of stuff, maybe just off to the side somewhere. So you can just draw those things for me. So you got 1, 2, and 4, and you know those things are wired in parallel. So, in series. So draw those out as in series. Okay, so 1, 2, and 4. And again, if you're watching this at home, I don't know if you can see this. I don't know if you can see it or not, but these guys are taking a look at the light box and drawing some circuits there. Okay, now next one. Ethan, give me a number that you want me to pull out that's not 1, 2, or 4.
Let's go 7.
7. All right. So what? Now you have to look and see what happens here when I pull out number 7. Zane, could you grab the one light for me? Give us a little bit more contrast here. See if that works. Way better. Okay. Number 7. Do you see what happened when I pull out number 7? 5 got brighter, 6 got dimmer. Would you like me to pull out? Now I know that 7, 5, and 6 are wired in some way. Would you like me to pull out another one?
5.
Okay, I'll pull out 5. Are you ready? 7 got brighter, 6 got dimmer. See that? Should I pull out 6? Hot. Ooh, it's hot. Why is that so hot? A lot of power being dissipated by 6, right? Pull out 6 and both 5 and 7 go out. All right. Show me how 5, 6, and 7 are wired based on that. See if you have that. So those 3 light bulbs are wired in some configuration. You try to see if you can show me how they're wired. Tougher one maybe than the 1, 2, and 4. Once you have it, share that with the person that you're sitting next to. See if that person agrees. Oh, Ethan, do you want to jump up and work with him?
Yeah.
If you want to, so you can share what your circuit looks like. And, who do we have there? That's Tracy. That's all.
Yeah, Tracy.
And then Kaya and Harper.
Yes, actually.
And True Love, yeah. True Love, I know. True Love was out. Did you guys get a chance to see the first robotics competition yesterday? We tried that during third hour.
Yeah.
We must have missed it, but
That's
pretty cool. All right, you guys got it wired? Would anyone be willing to show what it looks like? I'm just going to put it up here. Zane, does yours look good? Think you got it? We're not taking. Yeah, so I can. Yep. We're not taking. We're not gonna judge you if you got this thing wrong or not. But let's see. You got 6, and then you got 5 and 7 in parallel. Let's see. So you're saying 6 is everything flows through 6. So if I pull that one out, that should knock out 5 and 7. If I pull out 5, I notice that 6 gets dimmer and 7 gets brighter. See if that makes sense here. If I pull out 5, then the current from the circuit decreases because I've increased the resistance when I pull out 6. So, and then 6 and 7 become, or when I pull out 5, so 6 and 7 become equally as bright. And then if I pull out 7, the same thing happens. I like it. That's the way it should be wired. It looks like that works. Okay. Now, last one. If you didn't get that one, you're going to try this next one. We have 1, 2, and 4, 5, 6, and 7. What do you think are the other light bulbs that are wired together? 3, 8, and 9. All right, Schuster. Which one do you want me to pull out? Don't say 3. Oh my God. I mean, 3 is hot, right? All right. So pull out 8. Steven?
9.
Thank you. Is anyone going to make me pull out 3?
Yes.
Ow. All right. How's it wired? There you go. You guys got this one. Jack, can you reach over and grab those? We just pull out the red and black.
Yep.
Thank you. All right. Now, I don't know if that showed up on the video or not, but this next part will. So nice job with that. You guys, it's the same, basically the same thing as what Zane had on the other one. Which one was it that it was 3? That was the first one, right? Wait a sec. Wait. Does it have to be? Let me ask you this question. I don't know if this is if you guys are gonna agree or disagree with this one. So let's see. I like Zane. I like how you showed this. You went like this, and then you sort of showed it like this, and then you showed it like this, and there were some numbers there, right? So this was this one's 3, 8, 9, correct? That's how that was wired. All right. What if I had it like this? Would it be any different? Any difference in those two circuits? Doesn't matter where this thing is, right? This is 3, this is 8, that's 9. It doesn't matter where it is. It could become first, it could come second. It doesn't matter. Its voltage drop should still be the same, correct? Okay. How about this question? I call that position 1, position 2, and position 3. Sorry, position A, position B, and position C. And I'm going to call this position A, position B, and position C. I know that delta V across 3 is going to be the same regardless, but are the potentials going to be the same? Is A going to be the same potential in those? Is B going to be at the same potential in the C? Turn talk there, like if you're thinking about that volt on it, would that potential be the same? Turn talk really quick. Would they all be the same potentials? Go.
C would be the same with B.
B is different. A and C are G and C are the same. A and B is different.
Right.
Yeah, it's the same.
A is definitely going to be the battery voltage, correct? And C is definitely going to be the neutral or the 0, right? Okay. And then the question is, what happens to that B? Sort of hard to do that. You want to risk sort of explaining what you think on that? It's tricky. Go ahead, Steve.
Well, B in the first one is being changed because it's passing through 2 different, I'm going to say bulbs, because they're in parallel.
Mm-hmm.
So but B in the first one is going to be different than the other B because it's only passing through one bulb 3, because it's going through one bulb instead of 2.
Yeah.
Not in parallel.
Yeah, it's trickier, definitely. When I'm all said and done, if I go to this idea of going down some hills, right? The hill heights are going to be the same, but where you are on that, if I want to think of this as a series and a parallel, where you are on that hill, right? It could be something like this, where you have two of those and then you go down that last little bit. That doesn't necessarily have to be the same potential, but they have to have the same delta V's. Does that make sense? Okay, good. A little bit tricky. Honestly, I just made that question up on the spot and I'm like, ooh, could we answer it? I've done that before and other things too, and I'm like, oof, went down that rabbit hole, probably shouldn't have. All right, but hopefully that one helps. All right, let's take a look at this one, our last one that I want to do with you today. The idea behind analyzing complex circuits, so I'm going to go back to this for a second, is that you take any smaller segments within that complex circuit and try to break them into simpler circuit elements, redraw it, and then work backwards from the simplest one back. So it's a little bit time consuming, but it is a useful exercise to understand how to analyze complex circuits. A lot of times people question, they're like, well, why do we have all these different resistor values? I could pull in, that cupboard that I have hundreds of different kinds of resistors. You open up a circuit, some sort of complex electrical component, and you see all these resistors all over the place. They're control elements, right? So if I want to control how much current flows to particular things and I want to control the flow of energy, we use resistors for that. So we have to be able to take these circuits and analyze them. Now, we're going to try to determine everything. I want to know the current through R1, through R2, R5, R3, R4. I want to know the current through everything. I want to know the delta V across everything. So when we analyze these circuits, we're trying to find I and delta V for each component. Now, if I know I and delta V, can I determine power? Yeah, if I can determine the current and I can determine the delta V, I can tell you how much power is being dissipated. All right, so first thing, when you look at this, do you see two things that are in series? I often will look as far away from the power supply as I can and say, I see these two are in series. So I might start with saying, I'm going to take this circuit and I'm just going to redraw it. And unfortunately, this is somewhat time consuming to begin with. When I redraw that, I see that I'm not going to change those portions at all, but I'm going to replace this last portion, this portion here, I'm going to replace with a combination of 5 and 4. So I'm just going to write that as R45. Now this is 4, that's 5. I'm sorry, that's 3 and 4. Could you tell me how much that value is? It's 5 ohms and 15 ohms, so I add them together, I get 20, right? So this is now a 20 ohm equivalent resistance. This is still 60. This is R2. This is R5. This is R1. All I've done is I've taken those two and combined them into that. Now I have to redraw another circuit. Do you see anything that can be simplified from this arrangement? These two seem to be in parallel, right? So I can take that now and I'm gonna, so it's easier to follow as I work backwards through this, is I'm gonna take R2 and replace it with, I'm gonna take R2 and R34 and replace that with this one. Now this is 60. That's 20. When I take 60 and 20 and put them in parallel, you guys remember product over the sums? I could take, what would that be, 1200 divided by 80. I think I did that right. Right, this is again the product over the sums. 60 times 20 divided by 80. What is that equivalent resistance? 1 more time? 1.5? Thank you. Now I've got a 15 ohm resistance in series with a 20 ohm resistance. And that's also in series with a 25 ohm resistance. So now I have a really simple circuit, right? 3 things in series. If I wanted to do one more where I say, all right, I'm gonna go one more simplification, I can take any complex circuit and arrange it as a single power supply and a single resistor. So this is what we call REQ of that entire circuit. And I just add them all together, right? 25, 15, and 20. Is that 60? All right, so the equivalent resistance is 60 ohms, and this is a 120 volt supply. Now, I've taken this complex circuit and I've written it as the simplest thing. I would say that this thing sees, if I were to look at this here, it would see, I'm gonna draw a little eyeball here. It sees a resistance of 60 ohms. That's what it sees. Could you tell me how much current flows through? Now what we're gonna do is we're gonna work backwards, right? So I'm gonna change the color, makes it a little bit easier to sort of follow that. I would like to know the current flow through here, so I. You tell me what is I. 2 amperes. So it's delta V over R. That would be 2 amperes. Now I'm going to write that. That's would you agree that that's I1? I mean that's the current flowing through flowing out of the power supply, and it immediately goes right through R1, right? So our I1 is 2 amperes. What's I5? Can you make a case that I5 has to also be 2 amperes? Can you make that case? If 2 amperes is leaving that and then going to be split up in 1 Cs, are they going to recombine and go through there to be 2 amperes? Okay. So I've determined the current through 2 of those things. Now I'm going to take this and say, oh, let's go over here. Would you guys agree that that current is also 2? That current is 2? And that current is 2? This is a series arrangement, so the currents all have to be the same. Could you tell me what is delta V across this? What's delta V across that 25 ohm resistor? You have 2 amps flowing through 25 ohms. That'd be delta V is 50 volts. So I'm just gonna over here. I1 is 2 amps and delta V1 is 50 volts. I've determined everything for R1. I know what its potential is. I know what its current is. Do I know delta V across R5? It is 40. You guys did that bolt on, right? The potential difference across this now is 2 amperes through 20 ohms is 40 volts. Delta V5 is 40 volts. Can you reason through what delta V is across this? It's got to be 30. Could I also just take 2 times 15 to see that it's 30?
Yeah.
Oh my gosh, I know delta V across the parallel combination. To be, what do you say, 30 volts? You guys see it? Okay, now. It's a little bit harder. Now I have to go back up to this point, right? So I'm going up to here now. I would like to know the current through R2 and the current through this, right? I know delta V across these things. The delta V across this point right here is 30 volts. Because that was the equivalent of that. Do I know delta V across R2? It's 30, isn't it? You guys see that? Can you see it? Can I determine the current through here? This is 30. Can I determine the current through there? .5? I've got 30 volts going across 60 ohms, so I is delta V over R, so 0.5 amperes. 0.5 flows through here. Was there 2 coming in? Was that 2? And that's 0.5. How much must be going through here? That's got to be 1.5, correct? Whatever current comes in, it's going to be split up, so some of it goes here, some of it goes there. Wait a second, holy cow, let's look at this. This is 3 times the resistance as that, and it has 1/3 the current. That should make sense. All right? I've got I1, V1, I5, V5, I've got V2, I2. I still need to get these 2, correct?
So we make the assumption that I3 and I4 is also 1.5.
Okay, so do you see what Stephen's doing there? In order for us to do that, we're starting this way. We're going clockwise through the circuit to get it to the simplest thing. I'm sorry, I should have drawn that in black. We're going clockwise through the circuit to get the simplest arrangement of that, and now we're going counterclockwise to figure out what's in each one of these things. And what Stephen's doing now is he's making this last jump to say, let's take it over here. If that current is 1.5 amperes flowing through the parallel arrangement, or I'm sorry, the series arrangement of that, so isn't that 1.5 right here? Can I determine then I3? Can I determine I4? Absolutely. So now I've got I3 is 1.5 amps. So is I4 1.5 amps. Can I determine delta V3? What is the voltage drop across that resistor? It's 1.5 amps and it's 5 ohms. What do you do with those numbers? Just multiply them, correct? 7.5 volts. What is delta V4? 1.5 amps through 15 ohms, multiply those together. Is that 22.5? And it looks like if I did everything correctly, I've got 1, 2, 3, 4, 5. I've got all 5 components identified, right, with current and voltage. There you go. That's how you do it. Now it's somewhat time consuming. It's got some complications to it, but the process is just taking it from something that's complicated and make it simpler by going clockwise, and then go backwards through there to find that. Okay. Of course, we need practice. This is new to us. We haven't seen it before, but that's the process that you go through. I'm hoping the Volt-On sort of helped you understand voltage drop across things, because that's ultimately what we're doing there. And now from that, we just need to practice. Any questions for me before I stop the video? Go ahead, Zane.
It's just all the delta V's that add up to 1.5.
I think they do. I think they do. We got to be careful with that, because some of the delta V's are the same.
Oh, that's why.
Right? So again, it goes to the idea of potential. That like these, like when I go from this point to that point, the delta V across here has to be the same as the delta V across these. But the delta V across that and that have to add. So I know we have to be somewhat careful. I can't just you can't just take 50 and 40 and 30 and 7.5 and 22.5 and add them up, because they're not everything in series. There are some parallel arrangements. Is that the part that you were stuck on?
Yeah, I knew that there was a reason for it. I was trying to figure it out.
Good. I'm glad you are questioning that. Questioning things and like, wait, why doesn't this work? If there was just 5 series resistors, sure. Yeah. Good. All right, I'm going to stop the video there, and actually, I might actually have some of the whiteboarding on the video. I might do that so that people, if they're watching this, they can see that. I'm going to do some whiteboarding with you. So I'm going to have you close everything up there, grab a partner, grab a whiteboard. We're going to practice some of this stuff for the time that we're remaining. It's a good 20-ish or so minutes. So if you would, be expeditious in this, if you would, so that we can get through as many of these things as we can. So go grab yourself a whiteboard. Yeah, you can erase that. Yep. All right, and spread out a little bit except for that back table. So don't go to that back table.